So, I mean, this has quite a long history in that at the end of the 19th century, a guy called Edwin Abbott wrote a very famous book called Flatland, in which he kind of explored a flat universe. It was sort of social satire rather than physics, so he didn't go much into the physics of the universe. But subsequent to that, various people have looked at it. And most famously, a guy called Alexander Dewdney, who's a computer scientist in Canada, has gone through figuring out a lot of the physics of what a universe would look like if it actually only had two dimensions, whether you could actually make it work or not. Alexander Dewdney wrote a book called The Planiverse, in which it's a story about some people who accidentally start kind of communicating with the two-dimensional universe, and so he kind of explores the communication between universes and so on. But there's a load of technical appendices at the end of the book about what the science behind it was. And actually I read it, in the mid-1980s, just after it had come out. Somebody gave it to me for Christmas, and I was fascinated by this. It's one of the things that sort of inspired me about physics. And actually one of the things that just sort of made me think the most when I started doing this it's something very trivial. If you were a two-dimensional being living on a flat piece of paper, so you're a little stick figure living on a flat piece of paper, and you try and lift one end of a plank up, you can't do it, right? Because there's nowhere for the air to rush in. You're kind of creating a vacuum by lifting that end of the plank, because you've got the plank resting on the ground, and then there's you holding onto the plank. So there's no gap there for air to come in the way there is from the sides in 3 dimensions. So you can't do it. You can't even pick up a plank. And in fact, in this book, he had his characters having to kind of shuffle their feet up and down to sort of let the air in as they were lifting one end of things in order for that to happen. So it was just that trivial example got me absolutely fascinated with these things. And there's all sorts of stuff, like if you start trying to think about biology, right? Supposing you have a two-dimensional being, if it had a digestive tract, in other words, if it has a mouth going all the way down to the bottom, then basically it will fall in half, right? Because there's nothing holding the two halves together in 2 dimensions. And so you have to come up with some clever way if you want your two-dimensional beings to be able to eat and not fall in half. And so Dewdney came up with this idea of basically a zipper, because you can have a zipper in 2 dimensions. And so these creatures are kind of zipped together, and that allows things to kind of work their way down through their bodies. So it's a complicated world living in 2 dimensions. I'll give you one more example though, one more good thing. So an astronomical example, like astronomy in 2 dimensions and space travel in 2 dimensions. Turns out space travel in 2 dimensions is quite tricky. And that's because the concept of escape velocity doesn't exist in 2 dimensions, right? That actually it turns out that, in 3 dimensions, the force of gravity drops off like 1 over distance squared, which means as you go, if you go twice as far away, the force of gravity is 4 times as weak. If you go down a dimension, so it's only 2 dimensions, it turns out gravity only drops off like 1 over distance. So when you're twice as far away, gravity is still weaker, but only by a factor of 2 rather than a factor of 4. So that means gravity is a much longer range force in 2 dimensions than it is in 3 dimensions. And so that means that, so in 3 dimensions, there's this concept of escape speed. You can actually fire a rocket fast enough from the Earth, say, and it can actually escape entirely. In 2 dimensions, because the force of gravity is that much stronger, that much longer range, no matter how fast you fire your rocket up into space, it will eventually always turn around and come back. And that means, firstly, that actually you can't, deep space travel is very difficult, right? Because actually you have to put huge amounts of energy in to get far enough to actually get to the next planet. But worse than that, it means that actually the universe is sort of doomed, because the entire universe can't achieve escape velocity either. So a universe can't keep expanding forever and will eventually collapse back on itself. And so there will always be a big crunch in a 2-dimensional universe.
A lot of people are probably under the belief that our universe is going to do that.
So, well, life is complicated, right? Firstly, in our universe, in 3 dimensions, it doesn't have to happen. In our universe, there's probably this thing called a cosmological constant or dark energy, which is driving things apart. So actually, when I started thinking about this again for making this video, I started thinking, couldn't you do the same for a flat universe, right? If we introduce this cosmological constant, would that actually allow the universe to keep expanding forever? So I talked to my particle theory colleagues who are much cleverer at these kinds of things. Turns out that actually general relativity doesn't work in 2 spatial dimensions. That, or at least you can make it work, but it's very limited in that the concept of action at a distance goes away. In other words, the pull of gravity outside any body is 0. So actually you can't, if you live in a general relativistic universe, you can't even have gravitational interactions between bodies the way we do in our 3 spatial dimensional universe. So if you believe in general relativity rather than Newtonian gravity, which is what I was just talking about, then actually you can't build a universe at all with gravity in it, or at least not gravity in any way that we recognize it. So why bother to do this? Partly because it's kind of fascinating, and actually, if you like, you can think of it as sort of an exercise for scientists, because it's good to kind of think about things in ways you don't usually think about things, and that's how you kind of try and do new science, is trying to think about things in new ways. But it turns out actually there are 2-dimensional things in the real universe, and the most current example is this stuff called graphene, which is this sort of single layer thickness of carbon, new type of carbon that's been discovered. And it really does behave, because it's only a single layer of atoms thick, the electrons as they move around within graphene are really moving in 2 dimensions, which means that the physics of what's going on really is explained in terms of 2 dimensions. So there are physical systems that are of real current research interest, where understanding the physics of what goes on in 2 dimensions is really important.
It's really stuck with me, the idea of these 2-dimensional beings trying to eat and falling in half.
Yes.
And these other conundrums. If there are people who live in 4 spatial dimensions, will they look at us and laugh in the same way?
Sure, yeah.
Are there things about us that we're limited? What are we limited by?
I think they probably would. They would. How on earth can you exist in only 3 dimensions? It's so restrictive. You know, the number of things you can do in 3 dimensions. Here in 4 dimensions, we can do all sorts of clever things that they can't do in 3 dimensions. Another thing, if you start thinking about 2-dimensional and 3-dimensional beings, is the connections in the brain. Because in 3 dimensions, you know, it's quite easy to wire things up, and so you can actually wire all the neurons together. In 2 dimensions, it's actually a lot more complicated, because things have to cross over, and you've got to figure out how you can pass information where wires cross over and so on. And so actually a 3-dimensional brain is probably easier to design and probably can be more efficient than a 2-dimensional brain. Now, presumably, if you went up into 4 dimensions, things would get even more efficient, because the number of ways you can link things together gets, you know, that much bigger. And so presumably, you know, a 4-dimensional brain could be an awful lot cleverer than a 3-dimensional brain, and they would presumably pity us for our miserable 3-dimensional thoughts when they can have 4-dimensional thoughts.
I can't imagine how a 4th spatial dimension works. Can no human imagine that, or is that my limitation?
Well, in some ways that's the lovely thing about thinking about 2 dimensions, because actually if you start thinking about, well, how would a 2-dimensional being think about 3 dimensions, that at least gives you the beginning of an insight of how can a 3-dimensional being start to think about 4 spatial dimensions.
But there is no 4th spatial dimension.
Well, if you ask the particle theorists, they can tell you that sometimes you have 11 spatial dimensions, but most of them are very small. But no, for practical purposes, there are 3 spatial dimensions that we know of. Following the Earth around. There used to be lots of science fiction stories about L3. It used to be a popular place to put the anti-Earth, or, you know, if you're an evil genius, that's where you put your hidden lair, because it was always hidden behind the sun as the 2 kind of orbit around each other. We've now had enough satellites out there that have actually looked at the other side of the solar system to know that actually there isn't anything much at L3.